presentation is regarding our project on text summarization, where we performed a comparative study of various models. Text summarization is crucial in managing the overwhelming amount of textual data available today. Our study compares the performance of three widely used architectures, which are LSTM, BiLSTM, transformer model, and a hybrid model, on generating abstractive summaries. We explored how well these models handle context and generate meaningful, concise summaries. We used the BBC News summary dataset for our project. For pre processing, we performed contraction mapping to standardized text, after which we removed stop words using NLTK and finally performed tokenization with Spacey to break text into words. And as you can see in the distribution, we see that the average length is 191 tokens along the different inputs that are available in the dataset. Coming to our model architectures, first, let's talk about LSTM and BiLSTM. LSTM and BiLSTM are sequential models that learn patterns over time. This image that you see here represents the LSTM based encoder and decoder architecture for sequence to sequence tasks like text summarization in our project. The model uses GLOVE 300 dimensional embeddings to initialize the embedding layers, providing pre-trained semantic representations of words. The encoder processes input sequences using these GLOVE embeddings, which are fed into an LSTM. It outputs a hidden state and a cell state which summarizes the input. The decoder then generates the output sequence one word at a time by again using the glove embeddings with an LSTM and is initialized with the states that come in from the encoder. A fully connected layer projects the LSTM's outputs to the target vocabulary. Finally, teacher forcing is applied where we combine predictions with ground truth tokens to optimize training. Similarly, BiLSTM further enhances this by processing the sequence in both forward and backward directions, capturing additional contextual information, thereby improving the performance.
Let's take a look at the transformer model. The transformer architecture is built on encoder decoder framework. So it begins with encoder, then the input text is transformed into embeddings with positional encodings, and then it retains information from there. The encoder then processes this through multi-head self-attention, which captures relationship between words in the text, and then this is followed by feed-forward neural networks with add and norm and MLP layers, and the decoder, on the other hand, uses masked multi-head self-attention to ensure that the future tokens are not visible during training, and the final output is then generated by applying linear layer followed by a softmax function. For our hybrid model, we combine two stack layers of BiLSTMs. So it starts with an encoder that processes input text with positional encodings, and the text first passes through two layers of BiLSTMs. After processing the input and capturing the information, the output of BiLSTM is given to the transformer, which is the multi-head attention layer with add and norm and MLP layers. And this dual model is so that the model can help us capture sequential as well as global relationships. And for the decoder, our hybrid model follows the same structure as transformer.
Let's take a look at the results. The LSTM model achieved an average rouge and blue scores of 80.2% with a training accuracy of 50%. The BiLSTM model had improved results with rouge and blue scores of above 85% with the training accuracy of 77%, which is better than LSTM. The transformer model achieved near perfect scores with more than 97% for all the rouge and blue scores. The training accuracy was 99% with a low test loss of 0.52. Our hybrid model combining BiLSTM and transformer layers also performed well but fell slightly short of the pure transformer. It achieved 93% for Rouge 1 and L and a blue score of 86.3%. As we can see, the transformer model consistently outperformed all other models across all metrics. The hybrid model, despite its advanced architecture, came in the second place. The BiLSTM and LSTM models showed steady performance. An unexpected finding was the underperformance of the hybrid model. This could be due to its increased complexity, leading to potential overfitting, integration inefficiencies between components, or training instability. Our study concludes the transformer model has a superior ability to capture long range dependencies in text, making it the most efficient and effective choice for text summarization tasks. The model's efficiency and performance sets it apart from other complex hybrid models. So that's it about our project, and we thank you so much for this opportunity.